All right, yes, thanks for the opportunity to talk about this problem. As Oleg said already, this is about the hadronic decays of a light Higgs-like scalar. And this work was done a couple of years ago already in collaboration with Alexey Boyarsky and Oleg Ruchaysky. So let me jump to, so probably in this audience, I don't have to present a lot of motivation for looking for new physics, but still I find it helpful to have a perspective. So what we have at the moment is that our tool that we're using to investigate particle physics and physics in general is quantum field theory, and this is something that unites the principles of quantum mechanics, relativity, and locality. And it has been extremely successful, however, in many areas, in particular in, as I said, in particle physics as the standard model. But at the same time, we understand that standard model is not complete. And how do we know that? Yeah, we have several observations that do not fit specifically in the standard model. Like we do not understand what the origin of baryon asymmetry. We do not yet know what dark matter is or dark energy. We do not incorporate completely inflation. Gravity, of course, is not included, etc. So where do we look for new physics? One way to look for new physics is, of course, to build more powerful machines, right? And that would allow us to look at shorter and shorter distances and higher energies, and maybe new physics is hiding there. This one, and I think only this one, can allow us, for instance, to glean into the more fundamental structure of nature, right? Even to address the question of, I don't know, naturalness, or what lies behind, what are other layers of nature that we can discover. This is the way to do that. At the same time, as it's written in this plot, we have also uninvestigated corner, where new physics also may be hiding. And the reason we do not see those degrees of freedom or those particles that are hiding there is not because they are super heavy, but because they are weakly interacting with whatever we see, or with the standard model, in other words. So just to iterate, and this is, I think many people share the same attitude, we have to diversify our directions of search. In particular, we have to advance our knowledge along intensity energy frontier, so for like LHC or even larger colliders, and also we don't have to forget about intensity frontier. And as I said, if the coupling is very small, then that can be a reason why we haven't discovered those objects, those particles yet. The way to address this question is probably not to build very specific models or to commit to very specific models right from the start, but try to understand it in the most general way. And usually, what is done is that different particles, or what is called different portals, are considered that are mediating the interaction between the standard model and possible hidden sectors. And those portals are scalar, vector, axion, and so on. So in this talk, I'll focus on scalar portal, and why it is important. It is interesting to study it. Is first, we already see that there is at least one fundamental scalar. It's a Higgs. Okay, maybe we will discover that it's not fundamental, but at the resolution that we have now, it seems fundamental. Therefore, other fundamental scalars may also exist. Moreover, in many extensions of the standard model, those actually appear. Similarly, as we know, inflation is most probably driven by scalar. Scalars also appear as pseudo-Goldstone bosons, and for instance, like a dilaton. So there are several candidates for additional scalars that may exist in nature. So how do we now, let me go to specifics. So we consider an additional neutral scalar, which I denote by S, and the way to couple it to the standard model in order to preserve all the symmetries of the standard model is only through the Higgs. So we have this sort of mixing, and of course there may be some hidden sector with chi fermions that can be considered like candidates for the dark matter and so on. So if we diagonalize this Lagrangian, we see immediately that the interaction Lagrangian can be between the standard model and the scalar can be written in this way. So basically, we're trading the mixing between the Higgs and S for the interaction between this S and fermions of the standard model. Those are quarks and those are leptons. And of course, all the interactions similar to what happens with the Higgs are proportional to the mass of this particle, okay? So this is, of course, what happens in the UV. However, we're interested what happens in the IR. And if there were no strong interactions, we would just probably use the same Lagrangian because there are no there is no strong coupling. However, for strong interactions, it's somewhat more subtle. So for instance, integrating out heavy quarks results in the interaction of the scalar with gluons. And of course, we know that if we study processes at energies that are low, then these gluons, we cannot treat them as just perturbative. Okay, so if we do this explicitly, we integrate it out, then we can see that the Lagrangian, the new Lagrangian, or the effective Lagrangian of interaction is given by the following expression. So the way to, if you don't want to integrate it out explicitly, you may use a trick, and the trick is to use what is called a trace anomaly. And trace anomaly is given by the following expression. It's just beta function times g squared and sum over all quarks that are present. So everything that breaks scale invariance should appear on the left-hand side, because without any scale invariant terms, theta mu, the trace of energy momentum tensor, should be 0. And the beta function is given by this standard expression. So now what we do, we basically say, let's write the energy momentum tensor in different regimes. So above mass of MC, so mass of C quark, and below. Above it can be written with beta function where all the quarks contribute, and below we can say that, okay, we integrated out all the heavy quarks and all the light are there. Now, since theta that does not depend on what coordinates, doesn't depend on what coordinates we use, those two expressions should coincide. Doing this, we can re-express the sum of heavy quarks in terms of trace of the energy momentum tensor and the sum over light quarks. Plugging it back into the Lagrangian, we have this IR effective Lagrangian for the interaction of our scalar with the standard model. Theta is, of course, it contains all the fields in the standard model, and here we have 7/2 of sum of only light quarks. And also I defined 1 over Vs. This is the generalization of the VAV of the Higgs, which is of course effectively much larger than the Higgs mass because it's suppressed by the mixing angle, which is assumed to be small. All right, so what do we get here? Imagine that now, how do we detect this particle? We can detect it if it decays into the standard model particles, right? And we can look for the products. But for that, we need to understand what is the probability of this decay. So let's focus on quarks in perturbative regime and leptons in still perturbative regime. So if we consider, say, leptons, then obviously for energy, for masses of the scalar of order 1 GeV, the relevant channels are EE and mu mu. Obviously, mu mu will be dominated, will be dominating because, as we said, the interaction is proportional to the mass of the particle. Therefore, gamma into mu plus mu minus is given by this formula, which is just perturbative. There are no, so of course there are radiative corrections, but those are suppressed. Now, for hadronic decays, it is somewhat more complicated. So if the mass of S were extremely large, then the decay, say, into top would be similar, given similarly to this formula with just substituting m mu with m top. However, if we want to understand what is the decay rate into low energy degrees of freedom, which are kaons, pions, and probably heavier particles, we have to resort to some non-perturbative computation. So as we said in the IR, we have this expression for the effective action that we just derived by using the energy momentum tensor. Therefore, if we want to compute the matrix element of at leading order between, say, pi pi and S, then we have this matrix element where the following form factors were defined. Theta corresponds to the form factor of the energy momentum tensor, or better to say if it's trace. Gamma contains only U and D quarks, and delta contains S quark. So therefore, the corresponding decay rate is given by this formula. And so the long story short, what we need to know is just three form factors: theta, gamma, and delta. Unfortunately, we cannot access those very easily because we are in a regime where computations are difficult. We do not know, or not even difficult, we do not even know how to compute them from scratch. So one way to do that is, as we probably should do all the time, if we are below 1 GeV, we may hope that chiral perturbation theory may give us a decent approximation. So what do we do? So since theta is our G invariant, we can compute it using no matter what degrees of freedom, be it UV or IR. In the IR, what are the relevant degrees of freedom for this case? In the IR, we have only pions, right? For pion Lagrangian, we know how to write the pion Lagrangian. It's written in terms of this field sigma, which is just exponential of pi plus, pi minus, and pi zero, right, with some mass term. Now, expanding it in terms of 1 over f pi, we get Lagrangian that is given by this formula. And of course, we, as usual, identify this parameter b with just lambda QCD. So that m pi square is given by b times mu plus md. All right, so now we have the Lagrangian. This is effective Lagrangian, which is valid at certain low energies, right? So now we can find the energy momentum tensor easily, since we know the Lagrangian energy momentum tensor is obtained by using the Noether procedure, and we have theta mu given by this. As soon as we have that, trace of the energy momentum tensor is this. We can compute the corresponding form factor. It's given by S plus 2 m pi squared. Gamma can also be computed basically from here. Okay. And delta is 0 because there is no seq work that is present at leading order. Thus, the amplitude, putting everything together, we have that the amplitude is given by this expression. ms squared is what was here s. And as a result, we have the following formula. So this is the formula for the decay rate of the scalar into 2 pions, computed in chiral perturbation theory. Okay, and that was done a long time ago by Voloshin, of course, not in the context of the Higgs-like scalar, but back then people were looking for Higgs. People thought that Higgs may be, that was still in the time when Higgs could be light. So but how far can we trust this result? So just naively, what we would say that chiral perturbation theory works as expansion in derivatives over 4 pi f pi, so which is lambda QCD around 1 GeV, so around, yeah, or mass of rho. However, we can estimate it from the following expression. If we know how form factor gamma, say, depends on S, comparing this correction to the leading one, we can say where it starts dominating or at least becomes comparable. So people actually computed using next to leading order chiral perturbation theory and in lattice. So this parameter R square, which is called the scalar radius of the pion, it's 0.55 Fermi square or versus 0.61. And that corresponds to energies around 0.6 GeV where perturbation theory or chiral perturbation theory should break down, or at least not to break down, but to be not yeah. It should not be trusted. All right. So, but what should we do if we want to push the boundary even higher? What can we say about even more massive, guys? For that, we need to use some non-perturbative approach, and one of them is unitarity and analyticity. So how does it work? We basically say that all the form factors, which we denote by phi, should be analytic functions, with obviously a cut that corresponds to two particles that runs along real axis, and with the asymptotic behavior, which is 1 over S, which comes from just perturbative computations in QCD. So we basically have boundary condition. We have for large S, we have a boundary condition that there is a cut, and we know that the functions, all the form factors are analytic functions. Then we use optical theorem, which tells us that the imaginary part, this is just a pictorial representation of the form factor. Imaginary part should be the sum over all possible intermediate states of this. Similarly, the form factor that probably in a different channel times the scattering, right? What's written here pictorially in this form, we have just the formula. So imaginary part of phi is T, which is scattering, times phi, which is the same form factor, times some kinematic factors. Or similarly, we can do for the scattering matrix. Now, if the scattering is still elastic, this is just one channel, so the scattering can go pi only into pi, obviously for masses which are smaller than the threshold for multi-particle production. That corresponds, we have this expression, and therefore the form factor, every form factors are given by this, they satisfy the following formula, with delta being just the scattering of elastic scattering. If there are more than one channel, the S matrix is given not by just the exponent, not by just a phase, but there are actually two phases that correspond to pi and kk, say, and elasticity parameter eta that tells us how much the two channels talk to each other. So in one channel, we can solve this problem exactly. So let's look at this formula. If we have this formula, then we know that f pi, if it has zeros, we can factor out those zeros and then take the log of both sides, and that tells us right away that the imaginary part of the log is just a delta. We can, in the standard way, we can integrate over this contour, this log S, which picks up only poles at S because there are no other poles or zeros. And in the end, we get to this factor omega, which we basically denoted is the same form factor, but with all the zeros stripped out. So this is what's called the canonical solution. And then any form factor can be given by just polynomial times this canonical solution. For multi-channels, it's a similar procedure. However, it's not known in a closed form, but there is a theorem that there are as many canonical solutions as there are channels. But yeah.
Sasha, you have 5 minutes left.
Yes, that's.
You're half the slide through. Okay.
Look, I can skip some of them.
Yes, please.
Look, now taking into account this data that we have for this for pi, kk, and the mixing, all the approaches that they're using obviously only finite number of channels. So one of this approach is what's done in Donahue by Donahue, Gasser, and Lutwiller. They basically set up a numerical procedure to address this question. So they used some initial condition from chiral perturbation theory. They used data, and then they set up some numerical procedure, which leads to the following result. Their result is given by these black dots. The difference is just the difference in the data set for scattering data that they used from different collaborations. While in purple, here I show another approximation, which can be done by just approximating our scattering data with some resonance form. As we see that there is a huge discrepancy. There is some peak that they share, right? And this one is probably due to F0980, but below 1 GeV already it's a 0.8. The discrepancy is huge, and this dotted line represents the chiral perturbation theory. So we would rather expect that chiral perturbation theory works for here. However, according to Donahue et al., it doesn't work. So it's interesting to understand what's correct. So this is what we did. So we basically asked if this truncation is actually reliable. So the way to check it, we said, let's not use 2 channels, let's use just 1. And maybe we can mimic their result by appropriately choosing those polynomials that we were talking about. And indeed, you can do that. All the form factors you can fit. Their black is their form factors using numerical procedure, and in green it's our conformal factor. It's our form factor that we obtained by choosing properly those polynomials. And again, we also reproduce, or at least below 1 GeV, we are in good agreement with what they have for the decay rate. However, now we can ask ourselves whether it is reliable to do that. And everything hinges upon what is the actual behavior of the scattering data above 1 GeV. There we have many resonances, F0, 1370, 1500, and so on and so forth. And those a priori can mix a lot with pi. So we've made the following just as a model. Imagine that we assumed that this is the behavior of the scattering phase for pi. However, in reality, say it jumps by pi at another resonance of, let's say, 2500. Okay, then we see that actually the discrepancy is marginal, right? The only big discrepancy is close to the resonance. It's in here. So of course, if we zoom in, then it becomes more evident. However, this is not the case if we have if resonances, lighter resonances contribute. So if 1700 or 1800 contribute, then we see the discrepancy between what we would get by using this one channel expression and what we have in reality. Okay, so discrepancy is huge. On top of that, we should not forget that we have to satisfy 1 over s asymptotic behavior at infinity. Therefore, we will be forced to multiply by additional polynomials. And that introduces even more parameters, free parameters, which we can vary, and we can get for form factors drastically different results. So in green, this is what we predict if we pretend that we are oblivious to whatever happens above 1 GeV. But black, this is what happens in reality. So then the question becomes, okay, can we even trust this approach?
So, your time is up. So
I need to literally 2 minutes to finish this thing. So the way to cross-check what can be trusted, we can study what is called heavy quark systems, CC or BB, and there are in those systems there are 2 transitions, say psi to S, so first excited state into the lowest one with the emission of eta, and of the same state into the emission of J psi, which is the lowest state of CC system, with the emission of pi pi. One may argue that here the transition goes actually in two steps. First, it's QQ system that emits soft gluons, and then those soft gluons are converted into mesons. Therefore, the dynamics that governs the transition between psi and J psi, or this epsilon 2s and epsilon 1s, is independent of what is being emitted. Okay, so it's actually like using multipole expansion. So that allows us to factor out the strong coupling dynamics. Okay, so by doing that, imagine that we compute the amplitude of 2s into 1s and pi pi. It's given again by some matrix element of chromoelectric field times E1 dot E2. Those are polarizations of 2s and 1s correspondingly. And we can do the same with the emission of eta. Now computing the ratio, those coefficients that control strong coupling, right? The transition between 1s and 2s states, they drop out. And also assuming that here the leading contribution comes from theta pi of s, we can estimate the ratio between gamma eta and gamma pi pi, and then compare it with experiment and what we get from different models. So experiment gives us, say for BB 1.6, CC is 9.7, the same 9.7, and those are predictions from chiral perturbation theory, and this 2-channel result for Donahue et al., and this 1 channel that we discussed, the one with which we mimicked their result. Of course, the one that we used to mimic their result is pretty close to what they have. However, I would argue that chiral perturbation theory gives systematically closer results to the experiment. Okay, so it's like 1 versus 1.6 or 0.2. It's factor 5 less. Okay, or even here, 9.7 through 7. So I'm done. Basically, our goal was to understand how to compute, or at least to estimate the decay rate for this Higgs-like light scalar. And I would argue that the best thing that we can do is to use chiral perturbation theory. Of course, it's not reliable above. It would not give you exact result above 0.6, 0.5 GeV, right? However, it gives you for the order of magnitude, it's correct. While the result that is used, this analytic continuation and using dispersion relations, this one I would say that it's not reliable because this one heavily depends on what the UV behavior of scattering amplitude is. Thank you.
Okay, thank you very much, Sasha. It's interesting talk. Well, of course, not only because I work with it, but now I see that you kind of continue saying things in the direction that we had. In the interest of time, can we limit ourselves to 1 question? Yes. Yes, Marco. Can you? Yeah.
Yes, sorry. Yeah, sorry, my internet
Marco.
connection is not very.
Ciao.
Hi, Sasha.
What's up? I'm listening.
Oh, all right. So you mentioned several times the single channel approximation or something like that. So is that you just consider 2 pions in the final state?
Yes, exactly.
Because I would have expected that there are also states with many pions in the final
Yes,
states,
actually,
many
look,
light hadrons.
you're right. So, of course, look, it's like if S is below pi threshold, it does not decay into any hadronic states, right? Once it gets above 2m pi, the first channel opens up. Then you can even consider that 4 pions can be produced, but it's just experimental fact that 4 pi channels do not mix with 2 pi channels. It's just in the scattering, even in the scattering S matrix. Okay, so those can be neglected. So first, it's just experimentally observed. I do not know what the reason for that. But of course, one reason can be if you're close to just a threshold for 4 pions is just the phase space suppression. But in general, it's 2K becomes more important before 4 pi channel is important. Okay.
Okay, thanks.
Thank you, Sasha. Okay, so thanks again. Let's move on.